This presentation is on proof by induction. Now, basically, a statement can be proved to be true for all values of the positive integer n by showing, first of all, that it is true for n equals 1, or possibly 2 or 3, depending on where you want your starting position to be. And then, if it is true for n equals k, then it is also true for n equals k plus 1. This is called proof by induction. It's basically a domino effect where n equals 1 is true means that n equals 2 is true, which means that n equals 3 is true, and then n equals 4, n equals 5, and so on. For a series always takes a particular form. To prove that the sum from r equals 1 to n of f of r equals g of n, then part A, show that the sum from r equals 1 to 1 of f of r is the same as g of 1 by calculating both sides separately. Then part B, assume that the sum from r equals 1 to k of f of r equals g of k. Then C, use the fact that the sum from r equals 1 to k plus 1 of f of r equals the sum from r equals 1 to k of f of r plus f of k plus 1 to write down an expression that you can simplify to the sum from r equals 1 to k plus 1 of f of r equals g of k plus 1. And then, as you need to do at the end of any proof by induction, we need to write the standard closing statement. The n equals k plus 1 case is true, so by the principle of mathematical induction, the result is true for all positive integers n. So, an example of a series, we're trying to use mathematical induction to prove that from r equals 1 to n of r cubed equals a quarter n squared times n plus 1 squared. So we start with the n equals 1 case. So we work out the left hand side. The sum from r equals 1 to 1 of r cubed is equal to 1 cubed, which is 1. And then we solve the right hand side. A quarter times 1 squared times 1 plus 1 all squared is also equal to 1. So when n equals 1, the left hand side is equal to the right hand side, and so the n equals 1 case is true. Then we assume that the n equals k case is true, i.e. basically the formula with k's filled in is true. So the sum from r equals 1 to k of r cubed equals a quarter k squared times k plus 1 squared. Now we can do this because we know it's true for one particular case, that being n equals 1. So we can assume n equals k case is true because it works if the k is 1. Then, if we can use the fact that the n equals k case is true, means the n equals k plus 1 case is true, then we have got our inductive argument. Then n equals 1 is true, means 2 is true, means 3 is true, and so on. Now what we're aiming to show is that the sum from r equals 1 to k plus 1 of r cubed is a quarter of k plus 1 squared times k plus 2 all squared. Basically the same formula as the n equals k formula, but with all the k's replaced with k plus 1. That's what we're aiming to show. Common error in these sort of questions is to start with this, but we're supposed to basically start with the left hand side, the sum of r cubed, and rearrange to the right hand side. Now for a series it generally works the same way, so we start with the sum from r equals 1 of k plus 1 of r cubed, and we can split that up into the sum from r equals 1 to k of r cubed plus the sum from k plus 1 to k plus 1 of r cubed. Now from our induction hypothesis, we can replace the sum of r equals 1 to k of r cubed with a quarter k squared times k plus 1 all squared. And the right hand term, where the sum from r equals k plus 1 to k plus 1 of r cubed is just one term where we just stick the k plus 1 in for r. So we get k plus 1 all cubed. The next step is to simplify this so that it equals the form we had on the previous page. Now a quarter was a factor, so we'll use that as our first factor as we attempt to factorise this expression. Now if we look at terms in both expressions, k is only in the first term, but k plus 1 squared is in both terms, so we can factorise out k plus 1 all squared. And we open a square bracket, and for the first term, a quarter times k plus 1 all squared times k squared gives us our first term, a quarter k squared times k plus 1 all squared. Now to go from a quarter k plus 1 all squared to k plus 1 all cubed, first of all we're going to need to times by 4 to turn the quarter into 1. And then we're 1 k plus 1 short, so we'll also need to multiply by k plus 1. So we end up inside the bracket with k squared plus 4 lots of k plus 1. Then we multiply out inside that square bracket. So a quarter times k plus 1 all squared times k squared plus 4k plus 4. And then we factorise that quadratic. So we get a quarter times k plus 1 all squared times k plus 2 all squared as required. So that was what we were aiming to show for the right hand side. So the left hand side equals the right hand side. Therefore the n equals k plus 1 case is true. And by the principle of mathematical induction, the result is true for all positive integers n. So that's the structure of the argument for a series. For division, it takes a slightly different form. So to prove that f of n is divisible by x, first of all we do the n equals 1 case. So we show that f of 1 is divisible by x. Then for the inductive hypothesis, we assume that f of k is divisible by x. And then we rearrange f of k plus 1 so that f of k plus 1 equals a times f of k plus x times g of k. So since f of k is divisible by x, the first of those two terms is divisible by x, and the second one is x times something, so it also is divisible by x. And then we write the standard closing statements. So in this case, we want to use the method of mathematical induction to prove the expression 3 to the 2n plus 7 is divisible by 8 for all positive integer values of n. So look at the n equals 1 case. 3 to the 2 times 1 plus 7 is equal to 16. And 16 divided by 8 is 2. So when n equals 1, the function is divisible by 8, and so the n equals 1 case is true. We then assume that the n equals k case is true, so that 3 to the 2k plus 7 is divisible by 8. And then we look at the n equals k plus 1 case. So we want to show that the 3 to the 2 times k plus 1 plus 7 is divisible by 8. So as I say, we need to basically rewrite it so we get 3 to the 2k plus 7 somehow from that expression. So multiplying out that bracket, we've got 3 to the 2k plus 2 plus 7. Now what we can do with powers, we don't want 3 to the 2k plus 2, we want 3 to the 2k. But from indices rules, 3 squared times 3 to the 2k, we would add those powers and get 3 to the 2k plus 2. So I've split it off. So I've got 3 squared times 3 to the 2k plus 7. 3 squared is 9, so we've got 9 lots of 3 to the 2k plus 7. Now 1 lot plus 7 is divisible by 8, so I can split that off into 8 lots of 3 to the 2k plus 1 lot of 3 to the 2k plus 7. Now that first term, 8 times 3 to the 2k, it's 8 times something, so it is divisible by 8. 3 to the 2k plus 7, from our induction hypothesis, is divisible by 8. So the original is divisible by 8. Therefore the n equals k plus 1 case is true. By the principle of mathematical induction, the result is true for all positive integers n. And we do really need to write these down in exam questions to make sure that we get all the marks. Now for a recurrence relation, proof by induction takes yet another different form. So to prove that for u1 equals a, un plus 1 equals f of un, where a is a constant, that un is equal to g of n, first of all we show that g of 1 is equal to a, therefore by proving the n equals 1 case. Then we assume that uk is equal to g of k, and then we use the induction formula with k's rather than n, and then rearrange the required form after substituting uk equals g of k into the recurrence relation. And then we write the normal standard closing statements. So in this case, prove by induction that if un plus 1 equals 5un minus 8 with u1 equals 3, then un equals 5 to the n minus 1 plus 2 for all natural numbers n. Start with the n equals 1 case. We basically stick it into the formula, so u1 equals 5 to the 1 minus 1 plus 2, which gives 3. And since u1 is 3 in the question, we've shown that the n equals 1 case is true. Then we assume the n equals k case is true. And in this case, that would mean that uk equals 5 to the k minus 1 plus 2. Then we look at the n equals k plus 1 case, i.e. we're aiming to show that u to the k plus 1 equals 5 to the k plus 2. Now using the recurrence relation, un plus 1 equals 5un minus 8, so u to the k plus 1 equals 5 to the uk minus 8. We can then replace uk with the 5 to the k minus 1 plus 2. We then multiply out the brackets, so we get 5 to the times 5 to the k minus 1 equals 5 to the k. 5 times 2 equals 10, so we end up with 5 to the k plus 10 minus 8. 10 minus 8 is 2, so we end up with 5 to the k plus 2 as required. Therefore, the n equals k plus 1 case is true, and by the principle of mathematical induction, the result is true for all positive integers n, or in this case, natural numbers n. For recurrence relations, proof by induction always takes a particular form. So to prove that for matrices A and B of n, that a to the n equals bn, we calculate b of 1 and show that it's equal to a. We assume that a to the k equals b of k. Then we use the fact that a to the k plus 1 equals a to the k times a, and substitute a to the k equals b of k, and basically multiply out the matrices and rearrange the answers to the required form. Of course, we finish off by writing the standard closing statements. So in this example, we're trying to prove that minus 2, 9, minus 1, 4, all to the power of n equals minus 3n plus 1, 9n, minus n, 3n plus 1. So we start with the n equals 1 case. Minus 2, 9, minus 1, 4 to the power of 1 is clearly minus 2, 9, minus 1, 4. So the power of 1 just keeps it the same. Minus 3 times 1 plus 1, 9 times 1, minus 1, 3 times 1 plus 1 also gives minus 2, 9, minus 1, 4. So the n equals 1 case is true. We assume that the n equals k case is true. So minus 2, 9, minus 1, 4, all to the power of k equals minus 3k plus 1, 9k, minus k, 3k plus 1. Then we look at the n equals k plus 1 case. We're aiming to show that minus 2, 9, minus 1, 4 to the k plus 1 equals minus 3 times k plus 1 plus 1, 9 times k plus 1, minus k plus 1 in brackets, 3 times k plus 1 plus 1. And multiplying all those expressions out, the matrix becomes minus 3k minus 2, 9k plus 9, minus k minus 1, 3k plus 4. And that's what we're aiming to show. So we start with the left hand side and rearrange to the right hand side. So we start with minus 2, 9, minus 1, 4 to the k plus 1. We make it equal to minus 2, 9, minus 1, 4 to the k times minus 2, 9, minus 1, 4. Using the induction hypothesis, we replace minus 2, 9, minus 1, 4 to the k with minus 3k plus 1, 9k, minus k, 3k plus 1. We then do the matrix multiplication. So we get minus 3k plus 1 times minus 2 gives 6k minus 2, plus 9k times minus 1 gives minus 9k. we do minus 3k plus 1 times 9 to get minus 27k plus 9. We do 9k times 4 to get plus 36k. We do minus k times minus 2 to get 2k. We do 3k plus 1 times minus 1 to get minus 3k minus 1. And finally, we do minus k times 9 to get minus 9k. And we get 3k plus 1 times 4 to get plus 12k plus 4. And then we collect like terms, and we end up with minus 3k minus 2, 9k plus 9, minus k minus 1, 3k plus 4 is required. Therefore the n equals k plus 1 case is true, and by the principle of mathematical induction, the result is true for all positive integers n.